La, la, la. I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you for students. Just ask you to help us to use this the rest of the time we have today wisely. Lord, in your name I pray. Amen. All right, so get this out of the way. Stop wasting time with that. Okay, so let me talk about the solution to the quiz right quick. So problem number 1A. The easiest way to do a problem like this is to recognize what it is, which is a span. Span is subspace, so subset, subspace. A subset, which is a span, is a subspace, so that one's done. Problem number 2, this is just plain Jane subspace test problem. If you notice 0 times b is equal to 0, so 0's in there. It's a subset by its very construction. If we take two matrices in W and a constant, then we look at the linear combination of those like so. Because A1b and A2b are assumed to be 0, we get that C1A1 plus A2 is 0, which is to say that CA1 plus A2 is in W, which implies, of course, that a scalar multiple and a sum of two arbitrary elements of W is once more in W, which is to say that W is a subspace by the subspace test theorem. Part C, not a subspace. Variety of ways to show it. I chose to notice that a half is a scalar and 1 is a vector, right? Well, 1 is in the subspace, right? 1 is in Z. But a half times 1 is a half, which is not in the subspace. So that means that Z is not closed under scalar multiplication, therefore is not a subspace. There are infinitely many ways to disprove that being a subspace. You just got to do one. This here, W is in fact, yes, a real subspace of V. I again chose to present it as a span because it's just kind of the easiest way for me to express it concretely, the proof. And also the nice thing about this is it also gives you an indication. Say I was to ask a follow-up question, find a basis for W. Right? If you understand the calculation I've done here, then it's easy to find a basis for W as a three-dimensional real vector space. What's its basis? That, and that. That's the basis for W. I mean, technically, I suppose you should prove that this is linearly independent, but that's easy enough to do. Right? Set a real linear combination of these equal to 0. You can show that the coefficients of that linear combination are all separately 0, which would prove independence of that set, and hence that this is in fact a basis for W. All right, so again, it's a span, so it's a subspace. All right? But C, not a subspace. Because if you pick a particular element of W and you multiply it by a complex number, which is a scalar here, right? I is a scalar, then you're outside of W. Because if I multiply I times this, I get I minus 1, because I plus I squared is I minus 1. And aw, man, son of a motherless goat. That's supposed to be I. What is wrong with me? Oh, I know. It's Dr. Sprano's fault. He was talking to me when I wrote this. It's all his fault. It was Dr. Sprano's fault that you did bad on the quiz too? Okay. Sure, why not? Okay, so tell me so. That is supposed to be I, and that is supposed to be I, all right? Which means that W1 is not 1. W1 is in fact what? W1 is 0 in this world, because I'm using W1 as a notation here for that. So this is supposed to be I, which means it's actually 0 plus I. W1 is really 0 here. The conclusion remains the same. 0 is not equal to minus 1, so it's not in W. It's just the mechanics of my disproof are a little bit off. Sorry about that. Moving on here. Are these isomorphic? Yes. Here's the isomorphism. These are symmetric 3x3s. These are antisymmetric 4x4s. That's the isomorphism. Now, Did you have to write the isomorphism to prove that these are isomorphic? No. I did not actually say, find an isomorphism. If I'd said find an isomorphism, then this is what I'd want you to do. There are other strategies. Another way you could have argued here was to find an argument that the symmetric 3x3s were 6-dimensional, and the antisymmetric 4x4s are also 6-dimensional. Showing that you have two 6-dimensional real vector spaces is enough data to prove that they're isomorphic as vector spaces. So if you'd given me arguments that both of these vector spaces have the same dimension over the reals, I would be sympathetic to that being a complete solution here, given the instructions to the problem, right? So an even more complete solution, and you might have had time to do it, I don't know, is to prove that psi is both linear and onto and 1-to-1, right? If you prove, because that's what's missing for my solution as it stands, is I've just claimed this is an isomorphism. I actually haven't proved that psi so stated is an isomorphism. It is, but I haven't proved it, right? So there's that one. Problem 3. I hope some of you chose to do this one. I hope that the rank nullity tack on here wasn't enough to scare you away. It might have been. I don't know. Scary words, right? But this is definitely a skill that you need to learn for the test, right? How do you find the matrix of an abstract linear transformation? So again, it's whatever I put here such that t of, t beta gamma times the coordinate of v with respect to beta gives me the coordinate of the image with respect to gamma. So here, since gamma is the lexicographic basis for R2x2, some people would say the standard basis for R2x2, I can read from the formula that that's a plus b, c minus d, d minus c, a plus b. And over here, I might have tricked you, right? Maybe you put a, b, c, d here if you did it. You got to think through it, right? Basis is an ordered basis, so my formula is at odds with my basis. I did this on purpose to see if you're thinking.
Well, obviously we are.
This is why it's... Now, what would be unfriendly would be to do what? To just do it on the test, but not do it on the quiz, right? Yeah. But I did on the quiz, and I won't take off a lot. I mean, there's an alternative answer here, which is wrong, but very close to being right, right? If you put A, B, C, D here, I'm sure that's an answer I'll see if you did this one, right? It's wrong, but it's not terribly wrong. You've just found the matrix of the linear transformation with respect to a different basis, with respect to the x cubed, x squared, x1 basis. Yeah? Which is related but different. Now this, if you look at it, I think I would argue by just looking at this, you can see that this and that are the same row, right? And this and that are just, the rows are just minus each other. Or you could look at columns, right? The first two columns, one is a linear, is just a multiple of the other. The last two columns are identical. It should be fairly obvious by inspection here that the rank of this 4x4 matrix is 2. There are 2 linearly independent columns. If you don't see that, you could do the row reduction, but that costs you time, right? Time you might have on the test, but you certainly don't have on the quiz. But I would say by inspection, it's clear that the rank of this matrix is 2. And if the rank of the matrix is 2, we had a theorem that the dimension of the column space for the matrix with respect to any choice of basis is the same as the dimension of the range of the matrix, of the abstract linear transformation, which is to say that rank is an invariant concept. You can either calculate rank from looking at the dimension of the column space for the matrix, for the transformation given a choice of basis, or you can straight calculate the dimension of the range. Since I've already calculated the matrix, it's easy enough to see that the rank is 2, because the dimension of the column space here is 2. And once you know that, well, rank nullity theorem says the sum of the rank and the nullity has to be the dimension of the domain, which here is 4, so nullity is also 2. Right? Questions? Yeah.
So on the test, if it says find the rank and nullity, does that mean we don't have to find the dimension size of it, or does that mean
Rank is the dimension of the range. Nullity is the dimension of the kernel. So, yes. Now there's a separate, an interesting question we could ask, which is find a basis for the range of t Find a basis for the kernel of T. Those are other questions that I ask, but I haven't asked here. Yeah. And finding those would answer these questions as well by counting. Yeah. They're related, but different questions. Problem 4. R3 to R3, find the standard matrix of T. Here it is, I think. Again, Sperano was talking to me. I'm sorry I haven't written down more in this solution. I usually write down a little bit more, but I was in a really big hurry writing this in Convo today. I'm so sorry. I was trying to do this last night, and I just fell asleep. My bad. You understand? And I didn't have any whiteout, so sorry. Now, really, in some sense, Part B is like the mathematical equivalent of punched. I mean, this is a rude question to ask you, in some sense, because to get this question wrong, I'm sorry, but if you got that question wrong, it's not good. Didn't answer it. Let us not share with each other whether or not we understood this question. Listen, the fundamental theorem of, some people would say that, I don't know if this is, what's the fundamental theorem of linear algebra? There's a book somewhere that I've used that says the fundamental theorem of linear algebra is that, that seems more like a more interesting choice, but some people would say it's that every linear transformation can be represented by a matrix, and vice versa. So if I can calculate the standard matrix for the thing, that already reveals it's linear. So part A doesn't even make sense unless B is true. So this is the theorem. If T is linear, there exists a standard matrix for it, and the formula for the linear transformation is given by standard matrix times V. I'm talking, of course, about the context of column vectors, right? In an abstract vector space, we have to filter through the notion of coordinates as discussed in the previous problem. So yes, it's linear, because we just showed that the formula for it, and I haven't quite written all that out, but I mean, if I wrote a more complete version of A, you'd see that the formula for T is given by a multiplication by a matrix. That's what I really should write there. Okay? So I'll try to fix, I need to fix this solution a little bit and repost it later. Okay, I'll try to do that for you guys. Okay, and then is the part C was, is it surjective? Is it injective? Is it an isomorphism? The answer is no. No? Okay. That was, okay. So the determinant of T is the determinant of its standard matrix, and you can calculate that that's 0, which means that the standard matrix is not invertible. We had a theorem that a linear transformation from a vector space to itself was invertible, if and only if its matrix was invertible. And so seeing that this is non-invertible shows me that the matrix is, this is 0, shows me the matrix is not invertible, which means that T is not invertible. If T was invertible, that would mean it's both onto and one-to-one in this context. So it can't be either of those, right? Because it's not invertible. And we have a theorem, a linear transformation from a vector space to itself is one-to-one if and only if it's onto, if and only if it's an isomorphism. In other words, it's bijective with a linear inverse. So, you know, if this question, part C, gets more interesting when the domain and the codomain for the transformation don't have the same size. Then you actually have to think through it. Like, is it onto? Is it one-to-one? How do we check if a linear transformation is one-to-one? Look at the kernel, right? If the kernel is 0, the linear transformation is one-to-one. How do we check if it's onto or not? We have to see if the range is the whole codomain, right? And the mechanics of how you check that for a particular transformation depends on the formula and the context. If we're in the context of, you know, column vectors to column vectors, we can use row reduction stuff to look at the dimension of the column space and compare it to the dimension of the codomain. Problem 5. Find the coordinates of V with respect to the basis beta, 1, x minus 2, x minus 2 squared. So this, I wanted to draw your attention to something I've shared with you in homework solutions in various places, but it's an important calculational technique because it cuts through problems like this like a knife through butter. It's called calculus 2. And so this is Taylor's theorem applied to a quadratic centered at 2, right? I know that I can rewrite a plus bx plus cx squared as f of 2 plus f prime of 2 times x minus 2 plus 1/2 f prime prime of 2 times x minus 2 squared. This is Taylor's theorem. And these are easy enough to calculate because we know calculus. So f of 2 is a plus 2b plus 4c. F prime of 2 is b plus 4c because 2xc is 2 times c, which is 4c. And f prime prime of 2 is 2c. So you plug those back up in here, and it gives you this formula, which is all we need to see that the coordinates of v with respect to the 1, x minus 2, and x minus 2 squared basis are precisely a plus 2b plus 4c, 4 plus b plus 4c, and c. There you go. Now, did you need to know Taylor's theorem to calculate this? No. But if you don't use Taylor's theorem, it'll probably take you about 5 to 10 minutes. With Taylor's theorem, I can do this problem in under a minute. You're like, well, what does that matter? It matters because freeing time to think about things you're actually confused about is how you do well on a test, right? So, you're like, you mean the test is about time pressure? Yes. That is, in fact, what a test is about, time pressure. That is true. It is part of it. Not all of it, but part of it. T squared. So here, t is the composite of t and t, which is otherwise known as the twice differentiation operator. To find the kernel, we're looking for the solutions for f prime prime of x equal to 0. I guess the theme for problems 5 and 6 is calculus, right? So integrating this 2 times gives me that. Anyway, these are the things which are 0 by the second derivative operator, which means that the kernel is the span of 1 in x. So the fundamental tool for finding a basis for the quotient space is identifying how you can build a basis for the whole space, right, by looking at a basis for the subspace that you're quotienting by and other stuff. And the way to construct the basis of the quotient space is simply to take the extended basis, right? And you don't want these because these are 0 in the quotient because they're in W. So they're not linearly independent. Far from it. Anything that has these, bad. But these two, will serve to give a basis for the quotient. This is, in fact, this was the mechanics of the theorem which proved that the dimension of V mod W was dimension of V minus the dimension of W. The proof of that theorem basically involves this construction in the abstract. So that's how you do it. Yep.
Is it also like correct to think of it as like the elements that are in the span of the kernel are not going to be like the one in the x are the ones that are going to be left out?
Right.
Okay. So whatever the kernel span is not.
Yeah. Whatever's in the kernel is. It behaves like 0 in the quotient space. So we definitely don't want 0 in a basis, right? So we want the things which are non-zero in the quotient space. And we also want a linearly independent set which spans. So just mechanically, if you take the complement of the kernel basis for a given basis, that's going to, when you look at the cosets corresponding to those, serve as a basis for that quotient. Yeah. And I'm sorry I didn't have a question on the first isomorphism theorem on the quiz. I really should. That is part of the test. Make sure you know the statement. Yeah.
So when we're having a basis for like polynomials of order n, and you know how like, for example, like to the third
The basis, yeah.
Have like x cubed is the first term, and then it descends down to 1.
Right.
And because like the bases are different, even if it's the same terms, just flip in different orders. How do we know which basis to use?
Oh, there are infinitely many correct answers to this question.
Okay.
Yeah, I mean, I can switch the order. I could do like x squared plus x cubed plus w, x squared minus x cubed plus w. There's an infinite, so that's on me. I have to learn how to grade infinitely many answers. That's okay. Oftentimes there are many possible answers to a question. Yeah. Yep. Well, I'll see you guys Friday. I hope you did well. I hope everybody got their 40 points. I don't know why I did that. Now I have an inordinate amount of grading to do for the quiz. I'm an idiot.
0
fail forward.
I know I
Bye-bye.
got